Capacitor discharging and charging. Here we have a simple circuit involving a two-position switch, allowing us to charge and discharge this capacitor. With the switch in this position, the capacitor will be charging. There will be a brief flow of charge around the circuit, building up positive charge on the left-hand plate, negative charge on the right-hand plate. As long as the switch is in this position, charging will continue until the potential difference across the capacitor equals that across the cell. With the switch now moved to this position, there will be discharging of the capacitor. The charge will rearrange, passing through the resistor. On discharge, the voltage across the capacitor is equal to the charge on the plates divided by the capacitance. Also, the voltage across the resistor is given by the current times the resistance. But current is equal to the rate of flow of charge, delta Q by delta T. So we can write that the voltage across the resistor is equal to the resistance multiplied by the current, or multiplied by delta Q by delta T. But the sum of the potential differences in a circuit adds up to 0. So we can say that 0 is equal to the potential difference across the capacitor plus that across the resistor. They have equal magnitudes of potential difference in opposite directions. So we can say that the voltage across the resistor is equal to minus that across the capacitor. And so equating these two terms, we can say that R delta Q by delta T is equal to minus Q over C. Rearranging, we get that the current delta Q by delta T is equal to minus Q over RC. So this means that the rate of change of charge, the current flow here, is directly proportional to the amount of charge present, Q, on this term. In any circumstances, when the rate of change of a property depends on the amount present, we get an exponential change. So in this case, the graph of charge against time would show an exponential decay, something like this. This is the charge stored on the capacitor. If we call the initial value Q0, then when we get to a value Q0 over the exponential function e, roughly a third of our starting charge, drawing a line across, we get the time as being equal to the resistance multiplied by the capacitance. RC is called the time constant for a circuit, and it is the time taken for the charge to drop to 1 over e, or around a third, of its initial value. From this, we get the equation Q equals Q0 e to the minus t over RC, where Q is the charge at time t, Q0 the initial charge, R the resistance in ohms, and C the capacitance in farads. I've copied this equation forward to this next slide, and here again are what the terms mean. Q being the charge after time t, and that would be measured in coulombs. Q0 the initial charge, also in coulombs. R the resistance of the resistor in series with the capacitor in ohms, and C the capacitance in farads. The potential difference and current are both directly proportional to the charge on the capacitor. So we can also say that the potential difference V at time t will be equal to the initial potential difference V0 times e to the minus t over RC. We'd get a graph something like this of potential difference against time. Also, the current I after time t is equal to the initial current I0 times e to the minus t over RC, giving basically the same shape of graph of current against time. On charging, as the potential difference across the capacitor increases, the current reduces. The charging current therefore reduces exponentially in the same way as the discharging current. Here we have a circuit with a power supply with the potential difference across the supply shown here, a resistor, and this is the potential difference across the resistor, and here's the capacitor with its potential difference. Now at all times the supply potential difference will be equal to the sum of that across the capacitor and the resistor. As the potential difference across the capacitor increases as it becomes more fully charged, the potential difference across the resistor will reduce. Eventually, when the potential difference across the capacitor equals that of the supply, there will be no potential difference across the resistor and therefore no current. If we plot a graph of potential difference against time, we would get a reading something like this for the potential difference across the capacitor. It increases rapidly at first and then less rapidly. The resistor would show a potential difference something like this. It starts off with the full supply potential difference and reduces down to 0. So this line shows the potential difference across the resistor. The sum of the two lines will always be equal to the supply potential difference. If we measure the current in a capacitor-resistor series circuit, we could plot a graph of the current against time. We could then read off the graph the time taken for the current to drop to 1 over E of a particular value. This would then give us the time constant, as shown here. Here's our current against time graph, and we'd get a line something like this. If this was our initial current, if we find the value when we have 1 over E of the initial current, roughly a third of its initial value, and draw a line across, this gives us the time constant, RC. Finding the value from 3 different starting currents and taking a mean will give us a more accurate result. For example, we could pick another value, which I've called I1, and this comes out at this point. Then if we find 1 over E of I1, that would come out at this point. Finding this time here would give another value for the time constant. If we did this a third time and then found the mean of our 3 values, this would give us a more accurate result. Taking this expression again, we can use natural logs to get a more accurate figure of the time constant. If we take natural logs of both sides, well, when objects are multiplied together, their logs are added. So we get this expression. But the natural log of e to a power is simply the power. So we can write this. Rearranging to this format, we now have a variable is equal to a constant times a variable plus another variable. This is in the form y equals mx plus c. So if we plot a graph of the natural log of I against time, we should get a straight line of gradient minus 1 over RC and y-intercept of the natural log of our starting current. So here's our axes for natural log of I against t. We would end up with a negative gradient, the y-intercept natural log of our starting current. The gradient is minus 1 over the time constant.